Hello, my name is Mr. Whiteman, and in this session I'll be going through enthalpy change of formation in relation to Hess's law, and this is an energetics topic in A-level chemistry. In a previous video I went and spoke about average bond energy calculations and a bit further on Hess's law, so check out that video if you have not seen that already. But in this video we'll be focusing on enthalpy change of formation, and it will apply to other reactions in relation to enthalpy, but specifically just enthalpy change of formation. The level of maths that you need, as described in the previous video, is essentially if you had a length of string, how long would that piece of string be? Because all we're trying to do is work out that unknown if we are presented with, say, a total distance or total measurement. In that case, this would be 60. This is all the level of maths that you actually need in these calculations, but what's actually important is understanding the definitions in relation to, say, delta H reaction, delta H formation, delta H combustion, and any other enthalpy changes that you will encounter, because the definitions are required to be able to write the equations that are needed to make the Hess's diagram. So enthalpy change of reaction is the standard enthalpy change of reaction when a specific reaction and reaction quantities react under standard conditions and standard states. So what this is if we were unable to define a reaction as being, say, formation or combustion or anything else, it's just a generalized energy gap between two different energy states between, say, reactants or products. Enthalpy change of formation is when you form 1 mole of a compound from its elements under the standard conditions and their standard states. So, for example, forming methane, enthalpy change of formation for methane would be carbon plus 2 moles of hydrogen making 1 mole of methane. So per mole of methane formed, if you had a value for delta HF. Delta H combustion, if you were combusting methane, then that would be per mole of fuel of methane of when it combusts. So it's per mole of reactant, whereas formation, for example, is per mole of product formed. So understanding the definitions is quite important when it comes to balancing, because we need the right mole ratios in equations. And you'll be presented in exam questions data such as presented here, and you need to be aware of the say letter provided for you, so formation or combustion, or average bond energy, or delta HR reaction. So let's get started with some enthalpy change of formation. So I have a reaction generalized as being A becomes B, and I have some data provided for me in a table where it says enthalpy change of formation of A is minus 100 and B is minus 250. And from that information, you should know how to write the equations, because it's told you by definition what you need to be able to describe. So this is very generalized. So what I mean by this is elements forming A or elements forming B. So in these calculations, you may recall that you can use an equation such as this, where the enthalpy change of products minus the enthalpy change of formation for reactants would give you the reaction. And this is different to the average bond energy calculation, where it's reactants minus products. So this is like a cheat way of getting the answer fairly quickly, providing you are given delta HF formation data. If you are not given delta HF formation data, then you can't always just do products minus reactants. So you can do this because of, later I'll show you by the energy diagram as to why the maths allows you to do this. But to construct a Hess's law diagram, well, normally the reaction that we tend to investigate, or delta HR, would be written across the top. So reaction 1 would be A becoming B, and then my other reaction I'll call reaction 2, as provided by the data in the table. Delta HF of A is going to be forming element A, or compound A. So elements forming A is an enthalpy change of minus 100, and so elements becoming A is a route in which, as a reaction, elements become A, and so I write my arrow in this way pointing towards A, because that is the equation I'm trying to merge together with my existing one. So elements become A, and reaction 3 would be elements forming B, there's an enthalpy change of minus 250, and now I can complete my Hess's diagram because they are linked. So my elements can become B, my elements can become A, and A can turn into B. And so in an energy diagram, in terms of placement, if my A was arbitrarily at that level, to form A from elements, the energy change was minus 100, so it fell by minus 100, it dropped down exothermically to the energy point on which now is A when it turned into A. So it lost 100 bits of energy into the surroundings. To form B, it fell by a greater distance, so it must be linked because what makes A must be the same elements that make B, maybe in different ratios or different products, but it fell by a greater distance, so to speak, so minus 250, and so to get to B, it has to fall further, and therefore what we're trying to do is simply work out the energy gap, which you might say 150 if you were not paying attention to the direction of the arrow. So this is minus 150. So the total distance, so to speak, of this side must add up to the total distance on the right hand side, in this case 250, but what matters is the direction. So going down to minus 250, that'll be positive 250, and sometimes people say 150 should be incorrect, so that'll be for the reverse reaction, which is why we need to do products minus reactants, because if we do reactants minus products, then we get the positive change of 150 for the reverse reaction. So by virtue of where the arrows are pointing, if we were drawing this energy diagram and this Hess diagram, then we have to do products minus reactants to describe the forward reaction. You might have some teachers also say, if you go this way round the diagram, because we're going against the arrow, then we turn that into plus 100. We're going with the arrow, so we take minus 250, and so 100 minus 250 will also give us minus 150. So however you want to do your maths, either products minus reactants, or going around the Hess diagram, or drawing an energy diagram and then working out what X is, you're all doing the same thing. Generally, it's just finding the gap between that point and this point from A and B. So you can only do products minus reactants if you're presented with delta HF data. So another worked example. So this one is going to be the combustion of methane to form CO2 and water. So technically it can be described as enthalpy change of combustion by definition, because I have 1 mole of reactant of methane, but it could also just be vaguely placed as delta H reaction. So enthalpy change formation data is presented in the table on the right hand side. So from my elements forming their compounds, we need to respect per mole amount. So every time the reactant methane is formed, that is minus 75. So that's only one of them, because it's 1 mole of methane. There's 1 lot of CO2, so that's minus 394. And there's 2 lots of water per mole, so minus 286 times 2. There isn't a value for oxygen, and we'll come back to that. But if we did products minus reactants, we would then... Oh, there's there. So there's no energy change for oxygen, I thought that's coming later. There's no energy change for oxygen because it's already an element. You can't have it go from element gas to element gas with a change of energy, because it's on the same energy level, so to speak. So you don't have one, can't form oxygen, it's already oxygen, diatomic molecular. So the equation products minus reactants would give you the answer that you wish if you wanted to go by this way. And so if we were to calculate all of that, so products would be those values, and then minus reactants would be minus minus, because that makes that a positive, and gives us minus 891. And in an energy diagram, what this is saying is our elements fell by minus 966 total to form our products, and our elements fell by minus 75, so from the same energy point, to form our reactant of methane. Oxygen would have been the same, because as an element it would have been the same thing and in its standard state. And so we're trying to just work out what that gap is, and therefore we can work that out by finding the value by either just simply filling in the gap from the energy diagram there, or say products minus reactants would do the trick. In this case, 891 negative, because we're going down, otherwise positive if we're going in reverse, but we want the forward reaction. And again, you might have a teacher say, if you go against the arrow or with the arrow, so if I'm going this route around the energy diagram, in this case take plus 75, so plus 75, then minus 394, and 2 times minus 286 would also give you the same answer. Here's another worked example before I give you a set of exam questions. Calculate the enthalpy change of formation of butane given the following data. So in this reaction, we are actually presented with the enthalpy change of the reaction, and just utilising products minus reactants can be quite useful, because then we can just rearrange the equation. So to construct the Hess diagram, these are our elements that form butane, and that is what we're trying to work out. It says calculate the enthalpy change of formation of butane, which by definition is forming 1 mole of butane from its constituent elements under standard conditions. So we need to find that root per mole of butane. We are presented with that data to make CO2 and to make water. And we're also presented with the enthalpy change of reaction, which is minus 2877. So reaction 1, I would say, is the butane forming CO2 and water. Reaction 2 would be my elements forming the reactants, which in this case is what I want to work out. And reaction 3 is forming my products from my elements, and then I can construct a diagram to be able to calculate this, or I can do products minus reactants. So I'll go with my diagram on this occasion. So the energy level diagram will place elements at the top because the values are negative at this point. I could always adjust it if it was ever going to be endothermic, but I can calculate from my total of products that it's going to be minus 3006. So that is the minus 394 times by 4 and minus 286 times by 5 together. So it fell by a total of minus 3006 to make my 4 CO2 and 5 waters as my products. And then also I am presented with my reactants becoming products, so that is minus 2877. So it didn't fall as much, therefore it must have already started lower down. And so the energy gap I'm trying to work out is therefore reaction 2, which is that change. So my total distance, so to speak, is 3006. And so all I'm doing is trying to work out from this piece of string is that part. If I know this part, that being minus 2877, then I can work that gap. And so doing products minus reactants, if I substitute in the right values and then rearrange to find my unknown, in this case x, then I would get a value of minus 129, which I would also get if I did that distance, so to speak, that energy gap between the elements forming reactants. So here's an exam question. There are 2. See if you were paying attention. And at this point, you can also pause the screen to have a go yourself. But to also help you out, I will give you the equation that is needed, which is down below. So reactants forming products. You may recall that this was a similar question in another video of mine, but this time we are using delta HF formation data opposed to average bond energy. So the answer will come soon. And now, so the answer for question 1 would be A, oxygen is an element. So the enthalpy of change formation for oxygen is going to be 0 because there's no change in energy. By definition, it is already an element in its standard state. So there will be no change. That's why it's 0. Just be aware of that. And for question 2, reactants and products are going to be my ethane thiol plus oxygen and turning into CO2 and water and sulfur dioxide. To form them from their elements, I can construct a Hess diagram by having my elements there. So elements forming my reactants and elements forming my products, and just putting the values in. So forming my reactants would be minus 46, and forming my products would be a total of minus 1811, because there are 2 lots of CO2, 3 lots of water, and 1 lot of SO2. So So that's why it's 2 times minus 394, and 3 times minus 242, and 1 lot of minus 297. And so you can go around the diagram if you wished. You can go, say, do this route. That'll turn that into the endothermic route, which is plus 46. And plus 46 minus 1811 would give us a value of minus 1765 as our answer. Or we could products minus reactants. So minus 1811 minus 46 would do the same thing. And that's it. So check out the other videos for more chemistry support, and have a good day.